Hi everyone, I'm Anson. I'm a senior international student. I'm majoring in computer science. I'm from Hong Kong, and this year I'm very glad to come to UNC to work with Professor Manocha. Thank you. And I came here to work on cloud simulation and robotics. Today I'm going to talk about two projects which are related to synthetic data for cloud and video understanding. And because of the time limit, I think I'm going to talk about the first one. Okay. So this project is called LCAV, which is generating labeled videos for simulation-based cloud behavior learning. And LCAV actually stands for labeled cloud videos. And the main contribution we have here is we propose a novel procedural framework to generate labeled videos with a very large number. And then we improve pedestrian detection results by augmenting the view training dataset with our LCAV synthetic dataset. Okay. So what is cloud understanding? There are several applications for cloud understanding. For example, pedestrian detection, which is very important in autonomous car driving, where the car is needed to be able to detect every single pedestrian. Density estimation, where we want to estimate the distribution of people over time in a specific scenes. Crowd counting, which is we want to know the exact number of people in specific videos or scenes. Abnormal detection, which is very useful for surveillance. In crowd checking, we want to check every single pedestrians, and then we may be able to predict their trajectories. Okay, so for the network, for machine learning to work, we need to feed the network with some data. So traditional training, they use human annotator to annotate those unlabeled videos, and it takes a very long time for them to do that. To illustrate how long it takes, I copy here. So it takes really, really long to do it. Okay, so assume we have 1 hour video with 30 FPS, which is 108,000 frames. And let's assume there are 100 persons per frame, or 10 actually. Then it produces 2 million annotations. And then let's assume a person can annotate 500 annotations for a single image within an hour. And it takes 4,000 man-hours to do such a task. So 1 hour video, we need 4,000 man-hours. But with our approach, it is fully automatical that we have 108 5-minute videos released, which is equal to 10 million annotations. And the main point is the whole process is fully automated. So if you look at the left image, you can see this is an image annotated by human annotator, where actually it is not that accurate, because as you can see, when as we want to annotate the people at the back, it's very hard for us to do that because the head is relatively small. And then also, if you look at the people at the front, it is not accurate at all. But with our framework, because we know everything about the agents we generated, so we will be able to tell the exact location, the bounding force, to indicate where the pedestrians are, and also we will be able to tell how many pedestrians exactly there are each exit. So for example, this image, there are 858 pedestrians in this image. Okay, so I'm going to talk about the overall framework of our LCAV generation. So we have 7 parameters, and also 1 more parameters for our variation, which is the noise. So our framework is divided into 2 major parts, which is procedural simulation module and procedural rendering module. So to begin with, we first provide the parameters to our first procedural simulation framework, which we provide the density of the people we want, we provide the pedestrian count, and we provide the personality characteristic. That means we want the agent to behave in such a way that we are satisfied. Okay, so once we pass the parameters to the procedural simulation framework, and then it computes the path and the goal selection, path computation, path adaptation, because each agent would need to avoid all other agents. So they will have to perform collision detection. They will need to perform. They will need to find the best path for achieving such a task. Okay. So after that, we will have some trajectories of those agents, and then we pass that trajectories into our next module, which is the procedural rendering module. And then we will also provide 5 more parameters. The first one will be the background, whether it is a real background or a fake background. Also, we provide some noise, some agent models, some lighting conditions, and the camera angle. I'll talk about those parameters a bit later. So after that, we'll have our resulting videos, which is a bunch of videos with different parameters as we specified. For example, the head location and bounding box, we will know that. And then we will have some more attributes of that video, such as how many people are there in that video, or the lighting condition, or the camera angle, and so forth. Okay, so here's an overview of the parameters. As you can see, we have 7 major parameters: the lighting condition, the density of people, the environment, the crowd behavior we want, the camera viewpoint, the background, and the pedestrian count. So, right. Okay, so here are some examples of varying such parameters. So, pedestrian count. So you can see different pedestrians count. Viewpoint, we have top view, we have front view, we have very far away or very close. Density, we want the people to be as dense as we want or very sparse. Right. Behavior, so because it is quite hard for me to represent the behavior in such a way. So as you can see, the people at the bottom right, they are acting aggressively because they looks like they're running or they're walking fast. Right. So lighting condition, it is very easy for us to do that, but it looks really, really important in the data set that you can see the top left image. It looks like it is at night, so it is very dark, while the bottom right is very bright. Environment, so we will have both outdoor scenes and indoor scenes. We'll have train station, we have crosswalk, as shown here. So we'll also have both real background and synthetic background. So for real background, how it works, so is that we replace the synthetic background with some real-world images, and then we can configure the camera angle so that it looks very natural. And noise, here we use some Gaussian noise to help with the machine learning part, because noise is very helpful in this case. Okay, so here's some analysis. So we analyze the impact of fixing one parameter on the result. For example, we fix the camera angle, and then we let all other parameters to vary. And we found that it is very important to vary camera angle. That said, if we set the camera angle, if we fix the camera angle, and then the performance will go down. Yeah. So here it is a precision recall graph. So let me talk about this graph. What is it? So precision, I would say it is the quality of the performance. So it is the number of correct result divided by the number of returned result. So it means that how accurate you are doing. And then the recall, I would say it is the quantity, which is the number of correct result divided by the number of total ground truth result. So it means that how many correct results you can get. So this precision we call graph. And so there's another term called FH precision, which is based on these two attributes. So you can see the yellow line here, it is very low in terms of the AP. So this graph tells us that if we fix the camera angle and the performance will go down. Right. So we also analyzed the result on pedestrian detection, which is one of the crowd understanding application. And here we analyzed two approaches. The first one would be we train the detector only with those real-world training data set. And the second approach would be we want to augment that data set with our own LCARI synthetic data set. And we want to see if our data set is helping it to perform better. So you can see the green line here that we train our data set, we train our detector on a data set called Town Center, which is the green line. And this is the performance with the AP 0.64. And then we add our own synthetic data set into that training data set, and the performance goes up to 0.68. And if we add more LCARI synthetic data set, and then the AP becomes 0.72. So it looks like if we add more synthetic data set to some existing real data set, actually the performance will go up. So in this case, we can conclude that our data set is helpful in this case. And I want to mention another thing is that it is very hard for us to get real-world data set because it requires a very huge amount of labor force to do that, and also time, and also I think there's some privacy issue in US to do that, right? So here we also tried our approach on another data set called Kitty data set, and it shows that there's also improvement. So for example, if you look at the yellow line, so after adding our data set, it becomes the pink line, the purple line, right? So varying the number of samples from the same scene as the data set, we observe consistent improvement of AP, which is the FH precision, by augmenting the training data set with our own synthetic data set. So here's some results. You can see, right. So to conclude, so there are some further improvement on our work. We can improve the rendering part, so by adding more 3D models, by adding more walking cycle animation, so those agents won't walk in the same way. So there are more variation, and then we can add more background scenes, so the data set become more rich in terms of variety. And also we can perform analysis on how to improve the accuracy, and also we need to think of a way to combine the real world data with the synthetic data. So it means that we need to find some way to customize the synthetic data set in order to best fit the real world training data set. So yeah, that is all I want to say, and thank you so much.
Any questions?
So when you train
Right.
with the synthetic characters added to the real characters,
Right.
and then you're estimating the precision on detection, okay? Did you do that with the original data set?
Yes.
Or are you improving performance on the original data set or on the augmented data set?
Right, so you are saying, we are trying to train the detector with training data set which includes our synthetic data set, and then we test it on their testing data set. So in that testing data set, there are no synthetic data. They're only real world images.
Good.
Right.
Thank you.